So I'm going to talk today about air-sea fluxes of CO2 in the Southern Ocean. And I worked on this research with Scott Miller at the University of Albany. And so just before I even start, at the bottom you'll see we've got 2 cruises posted on our website, and that's at the bottom. I will put that up again at the end. But so for this research, what we looked at, we put an unattended eddy covariance system on the bow mast of the Nathaniel B. So this ship, and because it was unattended, I went on the first cruise, but after that, nobody from our lab was on the ship. So these are the 8 cruise tracks, and the 2 I'm going to show today, and the 2 that are posted on the website are these 2. They're about a year apart, and the reason I'm showing these are they're going to be more useful for the topic at hand. They're sea ice, and we had good delta P CO2 for our CO2 fluxes. So to show these cruise tracks in relation to the sea ice, the red dot is our ship track, and the sea ice is the SSMI product that you can get off the NSIDC website. So you can see a lot of the time we are in or near sea ice. This is a pretty low resolution image, but we don't use the satellite data for our fluxes. I'll be showing you the imagery that we took. So, all right. So our objectives here were to measure turbulent fluxes of momentum, heat, water vapor, and CO2, and then to ask the question of what is the effect of sea ice on the exchange coefficients. So the formula at the top is kind of the heart of what we do. It's the CO2 flux equation. FC is CO2 flux. The middle portion is CO2 flux as measured by Eddy covariance. So it's the covariance of fluctuations in the vertical winds and fluctuations in CO2. So we measure that. And then the right side is the bulk formula. So it's K, gas transfer velocity, times solubility, times the concentration difference between CO2 and the water in the atmosphere. So for that, what we're looking for is the gas transfer velocity or the piston velocity. We don't measure PCO2 ourselves, but there's a system already installed on this ship. So we borrow that data from Taro Takahashi at Columbia. So we have all the parts of this equation except for K, so we can work backwards and get that. And then in terms of our equipment that we installed, on the mast we have 2 sonic anemometers, a open path gas analyzer for water vapor, and a motion sensor for correcting the winds. And below deck, we have 2 Lightcore 7200s, closed path gas analyzers for measuring CO2 and water vapor. One is dried, and that's the one we end up using for CO2 flux. Drying the airstream reduces the fluctuations in water vapor, so that effectively reduces the web correction to close to nothing. So what I was looking at for this research was sea ice. So our images were pretty important to figuring out where we were in relation to sea ice. We have 2 cameras installed on the ice tower, one pointed off to the port side, one to the starboard. And we take 1 image per second throughout all the cruises. So we have many images. So we use the automated method by Callaghan and White for whitecap fraction, but we also use it for ice fraction. So you can see on the right side, the top image is the image, the bottom image is the black-white image from that method. It doesn't work every time for ice, so we had to kind of go back and look at every interval to see if it worked. On the periods where it doesn't work, we could usually tweak the thresholds by hand and get something that looked right. So in terms of our white fraction versus U10, the red points at the top, those are when we were in ice. So you can see, we're between 0 and 100%, but there's no wind speed dependence like there is for when we were in open water. The blue points. So the blue points are open water plotted against U10, and you can see I overlaid a Monahan and White parameterization. So we think those fall somewhere reasonably, but what I'm really looking at is the ice periods today. So the ice periods, one of the reasons it was difficult is because we are in a lot of different types of ice conditions. So there was times where we were very newly formed ice. The top left, very thin ice. That doesn't show up well with this method. The bottom left, you can see we've got ice flows, but we also have lily pads there. So there's no actual open water there. But that will pull up as about 30% ice cover. It only gets the flows, the method. So there's a lot of going back to correct by hand. So then for these cruises, what we got in terms of meteorology, this is a plot of wind speed on the top, delta P CO2 in the middle, and CO2 flux on the bottom. So we didn't get, in the first cruise, we didn't get too many high wind periods, but we got a few on the second cruise, over 20 meters per second. But we did get very good delta P CO2 for measuring CO2 flux, sometimes greater than 200 parts per million. And our CO2 flux comes in pretty close to the Sweeney line most of the time, except for periods when we're in ice. So you can see over here we underestimate quite a bit. But I'll show you plots that kind of show that better in just a second. This is a plot of sensible heat flux on the top and momentum flux on the bottom, plotted against core in red. And we follow, again, pretty well, except for some periods where we're in sea ice, so here and here, where we come in very much higher. So we were out to sea for about 85 days. There were about 10,000 potential flux intervals. After selecting for relative wind direction, plus or minus 60, we lose about half. We lose another 1,500 for delta P CO2, plus or minus 40 parts per million. And then we get down to about 1,500 each for open water and ice. So we lose a lot of data, even on the cruises that we selected as our best cruises. So then to show you what we got in terms of our fluxes, this is momentum flux plotted against U10, and it's plotted our open water version, or open water points plotted against the core 3.5. So we're the black line plotted against the gray in core. So we came in pretty reasonably to the core values. But then if I add the periods when we are in ice, you can see the red line is 0 to 20% ice. Our momentum flux increases a little bit, and then the larger ice periods, it increases quite a bit. So as you just saw, that's expected. That's been found before by Andreas and others. So because the roughness of ice is greater than open water. So we expected this, but it was just kind of, it made us more confident. We had everything lined up right with our data. Then we did the same thing for the heat transfer coefficient. So this is the open water plotted against core again. And then if I add the ice periods, we essentially see with more ice, we have decreased efficiency of heat exchange, which is also what we would expect. But then what we really went out for was the gas transfer velocity, the piston velocity. So this is, our line is black in black. It's all our data that pass quality control. And it's plotted against Sweeney. So this includes ice and open water. So you can see we come in quite a bit lower than Sweeney here. But then if I select just for the open water periods, we end up coming closer to the Sweeney line, although we are a lot more linear than their line is. So, and then if I put on our ice bins, low ice cover, we see a slight decrease in gas exchange. And then as we add the other bins, we see more and more decrease in gas exchange until we're at roughly the 80 to 100% bin has almost no gas exchange on average. So that seems reasonable, although not everybody has found that over the past couple of years. So I think that's important. And then I just wanted to kind of as like my last slide here to just show there was a model that came out last year, Luce et al. And it was an air-sea ice gas exchange model. It was based on three main parameters. They calculate gas exchange as kind of the sum of the effect of shear stress, buoyancy, and mean square slope of the waves. And so I took this line. Both the first two, the shear stress and the buoyancy effects, are parameterized as functions of dissipation. And this is a plot I pretty much took right from their paper, which is a hypothetical curve for gas exchange or the gas transfer velocity against fraction of open water for just the shear stress component. And so what they saw is, with this model, they end up seeing, if you start at the right side, 100% open water, and you go up, I normalized their K values from their absolute values to, I just divided by the open water values so that everything was normalized to their open water gas transfer velocity. So on the right side, you've got 100% open water, and you've got K over K open water of 1. And then as you move over to the left, you go to 90% of open water, 10% ice. They would predict just a little bit of increase in gas exchange, and that was due to form drag from the ice flows in the water, and then they see a decrease from there. So I tried to replicate this with our data by doing a sliding window on our gas transfer velocities. In order to match theirs, I had to make all the wind speeds, I had to normalize them to a specific wind speed. So these are normalized to 10 meters per second U10. Otherwise, the wind speed bins would make this useless. But essentially here, when I take my data with the sliding window means, we see kind of a similar decrease from 100% open water to 0% open water. Although we don't see the hump there at 90% open water. But this is also going to be influenced by the K versus U that we normalized those values with. So I used our value, our curve I showed earlier, but if I used a different K versus U parameterization, for example, if I take our K, measured K values, but I plot them against, but I normalize them with the Sweeney curve to 10 meters per second, we actually do see a little bit of an increase at that 100% to 90% open water period. So we think this is interesting, but we still have a little bit more work to do on it to kind of check. This was a very preliminary result. So just in conclusion, we saw that increased ice cover increases the drag coefficient. It decreased the efficiency of heat flux, and it decreased our piston velocity. And that curve I just showed, we saw it was similar to the Lucid All model, but it's going to be sensitive to the K versus U relationship that we use to normalize the piston velocity. So, thank you. And there's the website again. So just questions.
Okay. Does anybody have any questions? Go ahead.
Yeah.
So during that experiment, and was anyone measuring biology in the ice?
No, well, not within the ice, no. The crew that was on there, so I was the only person for this project, and everybody else, it was marine biologists, so there were people doing studies of like phytoplankton in the water, but nobody was looking at the actual ice. Yeah. So yeah, for now we only have percentage of ice. We don't have any data on what type of ice it was, so that would be useful.
Significant impact on your CO2 flux.
Right.
Depends on what community you're in the ice.
Right, absolutely. Yeah.
Any other questions? Okay, I have one. So did you also have to deal with flow distortion?
Yes, we do, and so we see like kind of a really, we believe it. This ship hasn't actually been modeled yet, okay. So a lot of other ships have been modeled, and we think we see that same kind of pattern of deceleration at the bow, maybe acceleration at the top of the mast. I didn't really cover it today just because I was kind of just doing a comparison between, like, the flow distortion would be similar. I was just doing the relative difference for the ice bins, but it is something we're going to have to work on and look at closer.
Good stuff. Thank you very much.